Today we are going to learn about optimizing model serving with gRPC. You will understand how to implement and leverage gRPC for efficient model serving, focusing on reducing latency and improving throughput in model serving environments. Welcome to our exploration of optimizing model serving with gRPC. In this video, we will delve into the world of gRPC, a powerful framework that is transforming how we serve models in high-performance environments. gRPC, standing for Remote Procedure Calls, is an open-source protocol that is designed to facilitate fast and efficient communication between services. Unlike traditional REST, gRPC offers significant advantages in terms of speed and performance, making it an ideal choice for environments where latency and throughput are critical concerns. By the end of this video, you'll understand how to implement gRPC to optimize model serving, providing a more seamless and efficient user experience. Let's get started.
gRPC, or Google Remote Procedure Call, is a high-performance, open-source framework developed by Google. It uses HTTP/2 for transport, protocol buffers as the interface description language, and provides features such as authentication, load balancing, and more. Unlike REST, which uses JSON for data interchange, gRPC uses protocol buffers, a binary serialization format that is smaller and faster. This makes gRPC more efficient, especially in environments where bandwidth is limited or where performance is a critical requirement. Additionally, gRPC supports streaming, allowing for real-time data exchange, and offers strong security features through SSL/TLS, ensuring secure communication between client and server. These capabilities make gRPC a compelling choice for modern microservices architectures and high-performance model serving.
To set up a basic gRPC server, you'll first need to prepare your development environment. This involves installing the gRPC libraries and setting up the necessary tools, such as a compatible version of Python, Node.js, or Go, depending on your preferred programming language. Once your environment is ready, you can create the server files. Start by defining your service in a proto file, which will include the service definition and the RPC methods it exposes. Then, use the protocol buffers compiler to generate the server and client code. With the generated code, you can implement the server logic by extending the base classes and defining the methods as per your service requirements. Once implemented, you can run your gRPC server using a simple command line or script. Finally, test your setup to ensure the server is running correctly and can handle requests. This foundational setup is crucial for further implementation and testing of your model serving capabilities.
Protocol buffers are Google's language-neutral, platform-neutral, extensible mechanism for serializing structured data. They are a core component of gRPC, providing a way to define service methods and message types in a proto file. This file describes the service interface and the structure of the payload messages. To start, create a proto file and define your service using the service keyword, followed by the service name and the RPC methods it supports. Each method specifies the request and response message types, which are also defined within the same proto file. Once your service and messages are defined, you need to compile the proto file using the protocol buffers compiler, protic. This generates the code required to build your gRPC server and client in your chosen programming language. Understanding how to define and compile protocol buffers is essential for building scalable and efficient model serving solutions with gRPC.
Once you have your proto file compiled, the next step is to implement the server-side logic. This involves extending the base classes generated by the protocol buffers compiler and providing concrete implementations for the service methods. In the context of model serving, these methods will typically load a machine learning model, handle incoming requests, process the input data, and return predictions. To integrate your machine learning model, ensure that it is preloaded and initialized when the server starts, reducing the latency for each request. Efficient resource management is crucial, so consider using techniques like thread pooling or asynchronous I/O to handle multiple requests concurrently. Additionally, optimize your model serving logic to minimize processing time and improve throughput. This might involve model compression techniques or using optimized libraries for numerical computations. By implementing robust server-side logic, you can ensure that your gRPC-based model serving solution is both efficient and scalable.
To interact with a gRPC server, you need to implement a client that can send requests and receive responses. Start by using the client code generated from your proto file, which provides the stubs necessary to communicate with the server. To establish a connection, create a new client instance and connect it to the server using the appropriate address and port. Once connected, you can send requests by invoking the RPC methods defined in your service. Each request must be constructed according to the message type specified in your proto file. After sending a request, the client waits for a response from the server. Ensure your client is capable of handling various types of responses, including errors. Implement robust error handling to gracefully manage network issues, server errors, or malformed responses. Properly managing client-side requests and responses is crucial for ensuring seamless communication with the server and delivering accurate model predictions to end users.
Integrating gRPC with existing machine learning models involves several steps to ensure compatibility and performance. Begin by loading your pre-trained models into the server environment. This might involve using frameworks like TensorFlow, PyTorch, or scikit-learn, depending on how your model was originally developed. Adapt your model to work within the gRPC framework by ensuring that the inputs and outputs are compatible with the message types defined in your proto file. This may require pre-processing inputs and post-processing outputs to match the expected formats. Keep in mind that models may need to be updated over time, so implement a strategy for deploying new versions without disrupting the service. Consider using a versioning system or a C/CD pipeline to streamline updates. Finally, pay attention to performance considerations, such as the model's inference time and resource usage, to ensure that your gRPC service remains responsive and efficient. By carefully integrating your machine learning models with gRPC, you can leverage the strengths of both technologies to deliver high-performance model-serving solutions. Deploying gRPC services in production requires careful planning and management to ensure reliability and performance. Start by selecting a deployment strategy that suits your infrastructure. This could range from on-premise servers to cloud-based solutions like Kubernetes, which offer scalability and flexibility. Implement monitoring and logging to gain insights into the service's performance and detect potential issues early. Tools like Prometheus and Grafana can be used to track key metrics and visualize data. To handle increased load, consider scaling your gRPC services horizontally by adding more server instances. Ensure that your deployment is secure by using SSL/TLS for encrypted communication and implementing authentication mechanisms to control access. Finally, adopt continuous integration and delivery (C/CD) practices to automate testing and deployment, ensuring that updates are rolled out smoothly and efficiently. By following these best practices, you can manage gRPC services effectively in production, providing a robust and reliable model-serving solution. Even with careful planning, issues can arise when deploying and managing gRPC services. Common problems include connection errors, incorrect message formats, and performance bottlenecks. Start by identifying the issue using logs and monitoring data to pinpoint where the problem occurs. Use debugging techniques such as test clients or mock servers to isolate and reproduce the issue. Improving error handling in your server and client code can significantly reduce the impact of unexpected problems. Implement retries for transient errors and detailed logging for critical failures. Network performance can be optimized by tuning parameters such as message size limits and concurrency settings. Reviewing case studies of common gRPC issues can provide insights into effective solutions and best practices. By addressing these potential challenges proactively, you can ensure that your gRPC-based model-serving solution remains robust and efficient, even under demanding conditions.
As we conclude our journey into optimizing model serving with gRPC, let's recap what we've learned. gRPC offers significant advantages over traditional RESTful services, including lower latency, improved throughput, and robust security features. We've covered the essential steps for setting up a gRPC server, defining services with protocol buffers, and implementing server-side logic tailored for machine learning models. Additionally, we explored how to handle client-side requests, integrate gRPC with existing models, and deploy services in production environments. As you continue your learning journey, consider exploring more advanced topics like gRPC streaming and interoperability with other systems. We encourage you to experiment with gRPC in your projects and experience firsthand the benefits it can bring to model serving. Thank you for joining us, and happy coding.